is this possible to get the amount of current that is flowing from the base terminal to collector terminal or emitter terminal to collector terminal? So that thing can be possible. Yes, so that can be possible with the help of the equations that we are going to develop now. So let's see how we can literally calculate how much amount or how much charge carriers that are moving from emitter terminal to collector terminal. So we already stated that IE, which will be with the two component, so that is IPE plus INE. So let me show in the diagram. So IPE, INE. So we are literally going to find this IE. So how much amount of IE which is coming. Okay. So let me know from the diode equation, we know the formula for both of this. So let me write it. So as this is an emitter terminal, so area E, area E means the emitter terminal area plus Q. So dP by LP, as it is an P region, so I am taking majority charge carrier, that is here. So this is known as the P charge carrier in N region, that is constant. So we usually take the magnetic charge carrier of the nearby region. So that is what we have took here. So this equation I have already wrote in the diode equation. So please follow that lecture to know more about it. So this is VBE, the forward potential that we have applied, divided by eta VT minus 1, right? Plus the next equation that is here, so INE. So that is also same, AE Q DN LN NPO, right? So then this can be even written as E power VEB divided by eta VT minus 1. Okay. So let me now take the common terms. So which will be AEQ. So which will be the common terms. So let me group the other constants, that is dP by LP Ni square divided by Nd. So this can be written as the thing, right? So based on the mass action law, I can write this like this. Okay, Dn Ln. Then this one is the same, Ni square divided by Na. So these are a charge carrier concentration. There is a donor atom charge concentration. This is acceptor concentration. So if we term the common term, that is VEB divided by eta VT minus 1. So this is quite constant. Okay. So what we can do is that we can generalize these things. So this is the diode equation. So this is completely the diode equation. So we are going to change in the BJT. So how we can going to change in the BJT is that IE, which will be equal to AEQ. Okay. So dP means what? The P. So P is nothing but this one. So we can compare this with the base regions thing. As we know, this is a minority charge carrier things, right? So this can be now can be written, or this can be rearranged to the thing that is DE and LE. So the charge carrier which are present here to that thing. So DE LE plus Ni square divided by Ne. Okay, so this is fine, right? So then this can be written as emitter and next one is base. So dB LB Ni square divided by Nb, right? So this can be even this termed as this is as it is. So because the potential that we already take that to that reference. Okay, so I hope this equation is understood, right? So here there is no doubt, right? So let me take a new page where we already supposed to know the width of the B, which will be much less than Ln or Lp or anything that we are taking. So which resembles that We will be greater than Wb. Okay, so we know that this width can be taken. So now what we can do here is that, so as we know, this Le can also be written in terms of, let me convert this into W. So this can be written as We, this can also be written as Wb. Okay, so now what we are going to do is that we are going to neglect these terms. So We will also be smaller, Wb will also be smaller. So both are small. So even if We is greater than Wb only, but that will be prox equal to some micro that kind of things. So length will be very smaller only. So now what we are doing is that we are ignoring all the terms. So we are considering, we are going to neglect, for now this is greater. So we are going to ignore this term. So we are going to consider Wb alone. Okay. So this the IE can be now written as AEQ. So once we ignore the emitter term, then we will get dB divided by Wb Ni square divided by Nb. Okay. So which is equal to e power VEB divided by eta VT minus 1. So now this can be, this entire region, this can be written as ISC. So this is some saturation current or some kind of short form that we are taking. So that will be equal to IE, which will be equal to ISC e power VEB eta VT minus 1. So this is the emitter current equation. So similar to the diode thing, so we are getting emitter thing. So let me leverage this to all. So the thing is that in PNP transistor, so the thing we saw, right, the BJT is called as transistor. This is another one name because there is a two junctions there, right? So they will usually call this as a transistors. So in PNP, the concentration or electron contribution because of holes will be much greater than Ne. So we can directly take a understanding that IE will be proxy equal to IPE. So that can also be written as AEQ dB WB Ni square divided by NB. The thing, right, so we have saw here, right, so this is a NPN transistor. So that is what we had right here. So this is an NPN transistor. The thing, it will come like VEB divided by eta VT minus 1. Okay. If you take a PNP transistor, then what will happen is that INE will be much greater than IPE, right? So then IE will be proxy equal to INE, so which will be written as AEQ dB, the same thing only, because we know the width of the thing only remains same. So width of the WB only usually smaller, so this is NB. So e power VEB divided by eta VT minus 1. Okay. So I think you guys able to understand the current equations, right? So then we can make approximation to IC also. So IC now we are written as IPC plus ICBO. So this can also be now treated to IPC because there is one is a usually that will be nano or some micro level of current. So that thing we can ignore it. So you guys already know this difference. So it is a reverse saturation current of collector junction in collector base configuration when emitter is left open. So this definition is very important. So please make a note of it. So in the previous lecture, I have given a detailed examination. So now we are seeing some configurations on current movement, everything. So that is fine. So current, how much current flow, that's all fine. So some kind of ratios are there. So in a common base, so let's see, common base we usually mention as CB. In the CB, let's discuss the current gain formula. So how much current gain will happen? So thing in transistor we usually discuss is the gain term, the voltage gain, current gain, input resistance, output resistance. So these all are the parameters that usually discuss. So the symbolic representation will be alpha. So the alpha will be written to, usually gain means what you represent the output current to that of input current. So this can be written as, now we know that output current is IC and input current is IE. So this is what the formula of alpha. If you know both this term, then we can directly find out the alpha. Okay. So this is the some major this one of the current gain formula, current gain constant in the common base configuration. So this is one important parameter we will analyze in the terms of configuration with respect to this one. This one means that is a common base configuration. So even the emitter will have some ratio, and the common collector will have some ratio. Everything has its own benefit. Everything has its own application also. So one will be good at current gain, one will be good at voltage gain. So we will discuss everything detailedly in analog devices, and also I will give you some glance of idea over there. So before going to see, so let's see how the doping profile concentration will vary. So doping and size. So this is one of the very important question. So in gate 2023, I think 2023 or 2022, they asked one of the very important MSc question in this one. So there's a 2 more question. I think majority of students failed here. So let me explain that clearly. Okay. So we usually know in emitter that is heavily doped. So there is no discussion, that is heavily doped. So here there is no doubt that is heavily doped. So let me term that as a heavy. Okay, this is heavy. But this one we know that is slightly doped, because here we no need to excess holes to be created here. So the holes which are coming from here to here, that will be fine. Holes are electron, majority charge carrier will be fine. But this one we don't have any idea whether this is light or whether this is heavy or but the question asked in 2022 is that comparing to emitter, the concentration at base will be low, that we know, but comparing to collector, what will be the concentration at base? So this is what the question they ask. So that mean we are not aware of it. So the thing is that they given two options, one is light, one is heavy, another one is moderate. The thing is that this is moderate. Okay, so this is what the order: heavy, moderate and light. So this is the question that asks, plenty of students not able to find out. So we know the base region, the width of the base region will be very thin and width of the collector region will be large. So this large width is need to collect more number of holes from the emitter region, but we may not know this width. So this is also moderate. So this is what the order of doping and size in the thing in the BJT. So I am leaving this to you guys. So please go through all these lectures, and if you have any doubt, please post in the comment section so that I will be available to clear all. So thank you. Stay tuned for next lectures.